Let's do it. So it is a great pleasure to have Mike Langberg here with us for the installment of our CSSP seminar. A brief introduction. Mike got his degrees in Israel, starting with Tel Aviv University, then moving to Weizmann, where he got his PhD. Then he spent time as a postdoc on the West Coast at Caltech, and was on faculty of Open University in Israel for a good number of years. But about 10 years ago, he apparently decided that Niagara Falls offers better views of nature. So he moved to State University of New York in Buffalo, where he has been ever since. Mike started to work on network coding and its relations to from a computational perspective in particular, and then worked on index coding, spent some time on codes for flash memory, and then he started to work on the topic of today's talk, and that is capacity and other characteristics of communication channels that are somewhere in between the two extremes of the independent random noise and combinatorial errors, wherein the channel can insert whatever noise the adversary chooses to insert. For instance, causal channels, where the noise is based on the portion of the transmission observed at this time instant, and a good number of other models. Mike, apart from other things, also was an undergraduate advisor of one of the co-organizers of this seminar, Zitan Chen, who is here. And with that, Mike, I'll pass it to you. Please go ahead.
Yeah, okay, good. So thanks a lot. Thanks for inviting me. And, we're just talking with Prakash on the fact that this is one of the advantages of COVID, this fact that these seminars are so open to everyone and everyone can attend, everyone can give the talk. So again, thanks for inviting me. So yeah, what I'll talk about is coding for adversaries between worst case and average case jamming. And I should say that this is sort of based on a number of works over several years. I'll just mention some of the co-authors. Zitan Chen was already mentioned. He's a student or just finished his PhD in Maryland. Amitalok Batkli, Bikash Day, Shai Chaviv, Sid Jaggi, Anand Sorwate, Carol, Wang, and Yihan Zhang. So all these are collaborators that have sort of contributed. And I should have also written, especially now that this is going to be recorded, that this is the research is partially funded by the NSF, and it gives me also great pleasure to give the talk. So as requested, this is going to be a board talk. It's a little bit ambitious. I have quite a lot of material that I want to give. I'll see how much I'm able to give. The talk very roughly is divided into two parts. There's going to be a very broad, kind of vague, slightly vague, but very broad introduction on the area, on the model of study, and on in general on the results. And then I'll sort of dive into maybe more technical issues of the results. So there's going to be a feeling of broadness, maybe general discussion, that the technical details won't be completely clear, but then we'll dive into things that hopefully will make them a little bit clearer. And stop me, of course, anytime with questions, and I'll just try to address them. So, of course, we're talking about communicating over noisy channels, and the general kind of model is that we have maybe a sender, we're going to call her Alice, and she's going to communicate over a channel to Bob, and there's going to be some kind of a malicious jammer, or malicious or partly malicious, and we're going to name that jammer James. So James is sort of corrupting the communication over the channel. And in general, of course, in this setting where we're going to have our encoders, our decoders, and the objective is going to be to communicate at high rate with low error. So I'll just write that very briefly. So we will have our encoder, and we'll talk about encoders later on a little bit in more detail, that just generate the code word. We'll have our decoders, and of course decode to the message. And our objective, just as usual, is we want high rate, and we want low decoding error. So high rate and low decoding error. And I'll speak a little bit about traditional studies. Right, so James is some kind of entity that's imposing an error. And there are many types of errors that can actually be looked at. I think one of the classical or the classical errors is one in which James is IID. So we can think of James just being an IID jammer, that it jams the communication according to some process which is irrelevant or doesn't take into account anything else except its random nature. So that's what I call the average case jammer, or the Shannon kind of model. So again, in that case, James is, I'll just write it here, is IID, and you can think of the binary symmetric channel, of course, as an example. And what I want to say is that this jammer is a very weak jammer. And that jammer is weak in the sense that it's weak in resources. So we can think of many resources that the jammer could use. For example, the computational complexity of that jammer is very, very small. It doesn't need to do any calculations when it's, if you think of the binary semantic channel, when it's imposing an error. So one resource could be computational complexity. Another resource of the jammer is the code that's shared between Alice and Bob. So Alice and Bob do have some code that they're using. And James, in this case of an IID jammer, doesn't really need to know the code at all. His jamming doesn't depend on the code. So again, he's computationally efficient. He doesn't know what the code is necessarily. And also, he doesn't have to look at the code word being transmitted in order to impose an error. So also, it doesn't have, or it doesn't need any view of the code word being transmitted. So that's a very, very weak jammer, and I'm just going to call that for shorthand. I'm just going to call that the Shannon jammer, or the average case jamming model. The other extreme is the worst case. And we're going to sort of name that the Hamming model. So that's a worst case jammer. And again, you can think of the binary setting in which I'm flipping, let's say, Pn bits. So similar to the binary symmetric channel, you can think of just having x equal to y equal to the binary alphabet, and James in this worst case setting is malicious, and it can flip exactly or up to Pn bits. So again, just like the previous jammer was a very weak jammer, this jammer is a very strong jammer in the sense of those all three parameters that I mentioned above. Right, so first of all, James needs to know, in this worst case setting, needs to know the code shared between Alice and Bob. So it needs a full knowledge of the code. It needs full knowledge of the code word being transmitted. And once it knows what the code word being transmitted is, and what the code is, it can very specifically design, of course, an error to sort of push the code word transmitted far away from it and close to another code word, so there could be a decoding error. So this task of finding the nearest code word and so on to push to is computationally is a computationally difficult task. So in all these parameters, actually, they're in this case, the jammer needs to be very strong in these resources. So these are the two extremes. Average case Shannon versus worst case Hamming, or a very weak jammer that doesn't do anything or need anything, and not the code, not the view of the code word, and not computational, and not any computations, versus this very strong jammer that needs these resources very strongly. And so what I want to talk about in this talk are models that sort of live in between these two worlds. So let me just write that. And there are many types of models that one could think of. So you can try to limit the computational complexity and kind of have some continuum between a very weak jammer and a very strong jammer. So I'm not going to talk about that at all, and that has been studied. Adam Smith and Venkat Guruswamy have looked at this. Ronen Chaltiel and a student of his have looked at this. So there are works that sort of limit the computational complexity of the jamming procedure. We've also looked at, over the years, of limiting the knowledge of the code in use. So again, a very weak jammer doesn't need to know actually what the code being shared between Alice and Bob is, and a strong jammer needs that very, very strongly. And you can limit the amount of knowledge that James has on the code. And maybe I'll talk about that very briefly later, using the notion of shared randomness and quantifying that shared randomness. But I won't talk about that either in this talk. And what I will talk about is trying to give different limitations on the view of the code. So I want to look at various models for James, for the jammer, in which his view is not very, very weak or not very, very strong, but some intermediate kind of view. So I'm going to look at models between these two extremes, and in particular, what I'll look at is limiting James' view. And I'll do this sort of, as I said, the talk is going to have one part which is kind of broad, the other part which is going to be a little bit more technical. And so the broad part, I want to present the model in a very general framework. And the general framework that I'm going to use is arbitrary varying channels, or AVCs. And after I present the model, I'll present some of the, well, after I present the model, I'll dive into a special case study of a specific model that's a simple one that can be sort of, I think, explained or give the intuition in a way that's that'll be, I think, nice to understand. And that's I'm going to do the case study of the binary erasure channel. Okay, so that's the plan. I'll start now with the model, and then I'll jump to the case study. And again, feel free to ask any questions. So let me kind of write the general model in slightly more detail than I explained previously. We have Alice, and we have Bob. And they want to communicate, of course. Alice is going to get a message. Bob wants to, of course, decode that message. And in the process of encoding, or in the process of communication, Alice is going to send a code word xn. And that code word is going to go through a channel, and our channel, given x, is going to give us an output y, but it's not only going to get x, it's also going to get a state s. So given x and the state s, which we'll talk about in a second, I'm going to get an output y. Of course, y is going to be fed to Bob. Bob is going to try to decode. And that state s, or Sn, is controlled by our jammer. Now, the thing is that the jammer either receives knowledge of the code word, or doesn't receive knowledge of the code word, or receives partial knowledge. So I'm going to draw it this way. So James, we're going to sort of play around with this limiting factor here that's going to control how much information from the code word is actually flowing onto James before James is able to design his jamming function. And again, a very weak adversary, or the Shannon adversary, is one in which there's no information at all going from X to James. And a very strong one is going to be one in which all the information from the code word xn is flowing to James. And I'll just maybe give an example here on the side, and that's the example we're going to sort of run with, just so it'll be made clear. If I think about the eraser channel, for example, I'll just write it down. So we have our alphabet X, or the alphabet of X and the alphabet of Y, and the alphabet of the state space is going to be just a binary alphabet. And we can think if James chooses a state which is 0, then the information is going to flow in the clear. And if James chooses a state which is 1, then we're going to do or output an erasure. So we can look at the channel, or write down the channel law as W of Y given XS is going to be equal to X, when A, let's say X if S is 0, and it's going to be an erasure if S is 1. So that's just an example for the binary eraser channel. But the research, or the questions in general, can treat any state-dependent channel. And the limitations we're going to look at are essentially two limitations. One was mentioned by Sasha. This is a causal limitation. So at time I in the process, so this causal adversary is going to behave in the following way, or this causal James is going to have the following information. Each and every time step, we're going to get some information communicated from Alice to Bob. And at time I, when James wants to choose the state, or the jamming state, his knowledge of the X vector is only X1 up to Xi. So let me just write that down. So at time I, James uses, or James' knowledge of the code word is only X1 up to Xi. So at time I, James uses X1 up to Xi when designing Si. And we're also going to look at a model in which there's some delay. So we're going to have a delta delay model in which the same thing at time I, we're not going to, James can't use X1 up to Xi, but he's going to use X1 up to Xi minus delta. So there's going to be a little bit of delay. So this model, I think, was referred to as AVC star in the Cesar Corner book. And as we'll see later on, even for the binary eraser channel, and even for just 1 bit of delay, there's going to be a big difference between the capacities. So that's one limitation that I want to talk about, which is the causal limitation on James. Again, James, when it's planning the jamming function or the jamming state, it only sees the history of the code word and not anything in the future. The other model for restricting the view of James is a myopic model, in which, let me do it like this. Maybe I'll copy this part. In which James is going to get a noisy version of xn. So James is going to get some, let's call it Zn, which is a noisy version through some channel. Again, this could be general, it could be a memoryless channel, it could be a memory channel with memory. But in general, we want to model a situation in which the information flowing from the code word to James is corrupted. So James is myopic. It doesn't see the code word very well, it sees it through a noisy channel. So in the myopic case, Zn is a noisy version of xn. And we'll talk about noisy versions through a memoryless channel. And you know, in the myopic case, you can think of being myopic and imposing an error in a way that's non-causal, or you can think of being myopic and also being causal. So you can think of having a non-causal or a causal model in this case also. Non-causal would be that James, before deciding on the vector, the error vector, the state vector, it actually sees the entire noisy version Zn and then makes a decision. And the causal one would be similar to what we have above, that at time I, it only sees Z1 up to Zi. Okay, so again, please feel free to, if there are any questions on the model. The model, I know it's a little bit, I'm doing it a little bit in general, but we'll sort of boil down to the binary erasure channel specifically in a second. I just want to mention more things that you could consider in this sort of area of study. And in general, in AVCs, one looks not at settings in which the power of both the encoding process and the power of James, the power of the corruption, is limited. So one can typically add both state constraints and these state constraints, there'll be some potential function, for example, on the states, and we want that to be less than some parameter. So in this case here, for example, if I look at the binary erasure channel and I want to only impose p times n erasures, then I'll just say that the sum of all the SIs is less than p times n. So that's very common. State constraints are very common. Maybe input constraints a little bit less, but you can also look at input constraints. Which is the same idea. I have some other potential function on the code words themselves. A little bit more in generality before I dive into the erasure channel. I talked about the encoders as just being a function that takes the message to a code word, but it's very beneficial in this setting to use not deterministic encoders, but rather stochastic encoders. And those would be encoders which take the message and some additional randomness of Alice and give us a code word. So let me shift up just a second because I want to use this picture. So the whole idea, again, intuitively, the whole idea is we want to utilize the fact that James does not know completely what's being transmitted. So one extreme was the weak Shannon adversary. The other extreme was the very strong Hamming adversary. And the difference in those cases was the knowledge of James of the code word being transmitted. And so we want to make an effort in the communication process to hide the code word from James. And so one method to hide the code word, that information being transmitted, is to add additional randomness in the encoding process. So not only is the code word a function of M, but the code word is going to be a function of M and some additional randomness of Alice. So that's very common in the sort of study or in the use of stochastic codes. And the philosophy is the more we sort of add this randomness of Alice, the more uncertainty we can sort of cause at James, and we can utilize this uncertainty to get a better rate, better than what we would have gotten if James knew everything. So we're going to use stochastic decoders quite a lot. And I'll also mention that, in general in the study of communication, if we think about decoding error, then we can have average decoding error, that is averaging over messages, or maximal, in which I take it maximal over messages. And at least traditionally in the study of AVCs and in other places, I can sort of ping pong between average case and max case by going between deterministic and stochastic encoding. So this stochastic encoding also helps me improve my decoding error from an average case setting to a maximal case setting. But we'll see later on that, at least in this context of these jammers that are intermediate between Shannon and Hamming, using stochastic codes is actually necessary to achieve capacity sometimes. So sometimes if you take deterministic codes, you really get a lower capacity, not only a different decoding error, but actually a lower capacity than what you would have received with stochastic codes. Okay, so I'm gonna dive in. That's sort of the model of study. And I know it's presented in a very general manner, but now I'm gonna present it actually just in the context of the binary erasure channel, and then we'll dive into the more concrete things that I want to show in the talk. But if there are any questions or anything, please feel free. Okay, good. Thanks, Sasha. So let's dive into the case study, which is the binary erasure channel. And we want a setting in which, just like previously, we have our code word is going to be communicated over the channel, but James is going to corrupt using either not doing anything or erasing. And so these, we're going to have these erasure symbols. And in all the models that I'll look at, the state constraint, or the number of erasures that I'm allowing, is going to be p times n. Or at most p times n. And so I want to write sort of maybe a high-level summary of what's known regarding the erasure channel and what we'll show in in this talk. And so here's an overview of the different sort of models. And again, I'll do this slowly. And if there are any questions, just shout out. So I'll start with the Shannon model, which is just a binary erasure channel in which I flip, or I erase an element with probability p. So in this case, James is just IID. And the error is chosen at random. So let's write here the capacity. So the capacity in this case is 1 minus p. It's achievable. Let's just do a random coding argument. So it's achievable using random codes, other methods as well. But just using codes that are chosen at random, each code with IID. And there's no, I'm going to have like a column here in this. I'm going to do a table. So there's no real need to prove any converse here because the converse is trivial. So the capacity is 1 minus p. The achievability is done using random codes. The converse, I'll just write down that it's trivial. You can never communicate a rate more than 1 minus p, of course, if you're erasing a p fraction. So that's Shannon. If I look at the Hamming model, then to communicate in the Hamming model, when I'm erasing a p fraction of the symbols, I'm actually looking for a code of a minimum distance pn plus 1. And so again, in this setting, James sees everything. And if it sees everything, what it tries to do, or what the jammer tries to do, is to erase, to confuse me as a decoder, and to erase all the symbols that I may differ for someone else. If my minimum distance is small, then I'm going to erase. I'll be able to do that. So I need codes. If I want to communicate, I need codes of minimum distance pn plus 1. And here the capacity is unknown, but we do have sort of, for the achievability, we do have a bound, and the same for the converse. So you can think of the Gilbert-Varshamov bound of 1 minus h of p in this case, which can be obtained either using greedy codes or random codes in a cleanup process. And there are various upper bounds. You can look at the LP bound or other bounds in this nature. And what I'll do is I'll just draw the bounds as a picture without really having this being precise. But the thing is that there is a difference between these two models, of course. So 1 minus p is, of course, this function. So that's Shannon. And Hamming, let's do it in red. There's a lower bound and upper bound, and they sort of look like this maybe. So there's a big difference between, of course, worst case and average case in this context. And now let's do a continuum sort of between these two cases. So the first column that I want to add here is something that we call an oblivious jammer. And this is actually the standard AVC model, which was studied, of course, by Prakash a lot and many others over the years. So in this model, and again, I'll maybe show just a picture of James. In this model, James doesn't have any information, just like in the Shannon case, here also, James won't have any information about the code word. Right, in this picture, actually, I should have this kind of drawing that I forgot. But in the oblivious case, James won't have any information. So why is the oblivious case different from the Shannon case? Well, here, the thing is that James will know the code shared between Alice and Bob. James will not see the code word. And we need to ensure that no matter which error that's imposed by James, we need to ensure that communication will be successful with high probability. The error is going to be chosen sort of once for any message being transmitted. So again, James has no idea which message is being transmitted. There's no knowledge at all, or to be more precise, James has no knowledge of which code word is being transmitted. And so once James has no knowledge of which code word is being transmitted, if we're looking, for example, at average error in calculating the decoding error, then what we need to verify is that for any error imposed by James, indeed communication will be successful, again, with high probability. So I'll just write that down. And again, if it's not clear, I can sort of explain. If it wasn't explained clearly, I can sort of go over that again. But James doesn't see the code word at all. And the code needs to actually work for any potential error pattern or erasure pattern that James will impose. So it turns out here, if I look at this oblivious setting, it's exactly like, or the capacity that you can get in this oblivious setting is also, in this case, it's also 1 minus p. It's also achievable by a random code. And as before, at least in this case, the converse is trivial. I'll talk about the converse in general, AVCs in a second. So again, just to be clearer, in the Shannon case, James is just imposing an error in an IID manner, irrelevant of anything that James may know regarding the code between Alice and Bob. And in the oblivious case, James, if it wants to, it can impose an error in an IID manner. But if it wants to, it can choose a very specially designed error that may actually impose a decoding error on a large fraction of messages transmitted. So potentially this oblivious adversary is stronger than the Shannon adversary. In this case, they're the same. There are many other cases in which they're the same, but there are also many cases, or there exist cases in which these two are not necessarily the same. So this is sometimes strictly a stronger adversary than the Shannon adversary. So I won't talk about proofs for the oblivious adversary at all, but what I will start now is talking about the causal adversary and then the myopic adversary. So in the causal setting, James, we were saying that it sort of, you can see, again, just as a reminder, x1 up to xi when designing, let's call this, well, I'll just use SI, that is when jamming the ith entry. And in this case, we'll see that this causal adversary is indeed stronger, specifically stronger than the oblivious or the Shannon adversary, but it's going to be weaker than the Hamming adversary. So what we'll show is the following. We'll show that the capacity in this case is 1 minus 2p. And if I allow a delay of just 1 bit, so if I think of James as seeing not x1 up to xi when corrupting, but x1 up to xi minus 1 when deciding on si, so it just doesn't see the current bit being transmitted. It sees everything before that except the current bit. Then we'll see that you can sort of jump to 1 minus p. So we'll do that. We're going to need to do that using stochastic codes, and I'll talk about that a little bit. And we're going to use list decoding quite a lot in the process, and I'll also talk about that. And the converse proofs are going to use a notion that's used standardly in AVCs, which is symmetrizability. And very roughly speaking, symmetrizability is the setting in which James tries to cause an error to Bob, and James does that by, if let's say X is transmitted, by choosing another code word X prime and confusing Bob between X and X prime. And he does that in such a way that if X prime was transmitted, then he can confuse between X prime and X. So there's like a pairing of code words, and this is stated very roughly, it'll be stated more clearly later. There's a pairing of code words that no matter which one of them was communicated, the jammer in this symmetrizability proof for converses tries to mix up the receiver between these two code words. So let me just draw that for a second. So I'll do this 1 minus 2p, of course, it's just that green line. So symmetrizability is also used sort of a lot in the characterization or in the study of standard AVCs. Here the converse is trivial, but in general you would need some kind of symmetrizability argument also when you're studying more general models, not the erasure channel. Let me just mention the myopic adversary, and then we'll go on. And again, if there are any questions, please let me know. So in the myopic case, James is going to see the code word through an additional noisy channel. And the noisy channel that I want to study is in itself the erasure channel. So what I'll look at in the myopic case is that James, let's say it sees this Zn, which is the noisy version of Xn, through the binary eraser channel with some crossover probability Q. So randomly with probability Q, elements of the code word are going to be erased to James. Based on that, James needs to design and encode a state vector or an erasure pattern. And here, there's a lot, it depends, the relation between Q and P come into play. So we'll talk about that a lot. So the capacity is going to depend on the relation between P and Q. And so I won't write down what the capacities are because we'll talk about them. But just like in the causal case, we're gonna, our encoding schemes are gonna be strongly tied to stochastic codes. Some of them are gonna have to be stochastic to get the rate that we talk about, and also they are gonna use this decoding. And I'll just again mention that the converses have the same kind of symmetrizability feeling to them, which I'll talk about again a little bit later.
Michael, this is Prakash. May I ask a question, please?
Definitely. I've been waiting for questions.
Okay, Michael, the myopic case is a bit of a non-standard case. Here, of course, the codeword is being constructed for transmission over the regular channel, but then it also has this feature that the idea is to confuse James. James the jammer, I guess that's why you called jammer James, is it?
Yes, yes.
Now, you use stochastic encoding. There is no stochastic decoding. In other words, there's no shared randomness between Alice and Bob, right, in all these models.
Yeah. So I didn't mention that sort of too explicitly, but I will. It's very common to look at these models in which Alice and Bob share a common randomness. And we've even looked at that, and we've tried to quantify the amount of common randomness shared between Alice and Bob and how that affects the capacity. Mm-hmm. But here, no. So the randomness used by Alice is only known to Alice, not to James and not to Bob. Mm-hmm. There's no common randomness.
Okay. All right. Okay, thanks.
Okay, good. Yeah, this is going a little bit slower than I expected, but I'll still try to, I hope I'll be able to do something concrete. Good. So what I want to do now, so these are the models in general. Again, if there are more questions, please ask. Let me talk about, because the proof techniques that we're using are very, very similar in the different models, and there are a lot of models here. It's, as you can see, even for the binary erasure channel, this is a very rich setting. We can choose, in the myopic case, we can choose different noise versions to James. In the causal case, we're looking at causality or causality with delay. You can combine myopic and causal. So it's a very rich family of problems we've been sort of enjoying and looking at them over the years. But because they use pretty similar techniques, let me talk about the techniques a little bit more before I dive into, let's say, one or two of the models and show the precise encoding or decoding or converse arguments, because at a high level they have a similar nature. And so let me try to do that, and hopefully this will give some kind of high level intuition on how we're dealing with these kind of models. And again, I just want to emphasize that the philosophy in this entire study is we have a model in which James is weaker than the Hamming model. So the only way to utilize that is to design a code somehow that's going to hide the code word from James. Because if James in the process of communication can learn what the code word is, then we're just back to this case. Because James has learned the code word, so it's as if he's in the Hamming model. So we always have to hide things from James. So let me talk about the stochastic codes first, and then I'll talk about, or let me talk about achievability, and then I'll talk about how we prove the converses. As I said, we're typically going to use stochastic codes, and many of the codes is just a random code construction, but in stochastic codes, you can add this kind of stochastic nature, or you can add stochasticity to the code word in many ways. And I'll just show, that's maybe the common way, or one common way, and I'll show others that we use. So maybe method number one to add stochastic or to add randomness to the encoding process is, let's say that I have a message M. I can build a collection of code words that correspond to M. Maybe each code word is built in an IID manner. And now as an encoder, as Alice, when I want to encode M, I just choose one of these at random. And so this does cause uncertainty because there is a subset of code words all corresponding to M in which I can choose one of them. And so this doesn't lend itself very naturally to the models that we're looking at, because many times when the code words, or let's even assume that the code words, if they're chosen IID, then even seeing a partial part of the code word, or even seeing a prefix of the code word, can give me full information about the entire code word. Think of maybe having or communicating at a rate that's not too high. If we're in a setting in which the channel does not allow too high of a rate, then sometimes just the prefix of a code word can, because it was generated randomly, can give me a lot of information about the rest. So this method of using stochastic codes doesn't necessarily lend itself to the models that we're looking at. And we use the stochastic coding in one of two ways. So one way is to sort of generate for each message not a single code word, but again a family of code words. But now the generation of these code words are done in a tree-like fashion. So what do I mean? Here, what we're going to do is we're going to divide our code word, this is xn, into chunks. Each chunk is going to be, I don't know, not too large, let's say of size n epsilon, and let's say that they're like 1/epsilon chunks. Each chunk in itself is going to be this type of standard stochastic code. So we're going to have, like, for each message M, we're going to encode with randomness number 1 for the first chunk, maybe randomness number 2 for the second chunk, and so on. So it's going to look like this. There are going to be a bunch of code words corresponding, short code words corresponding to M for the first n epsilon bits, a bunch of code words corresponding to M for the second chunk of bits, and so on. And for each, when I encode the message M, I choose one in each place. This generates a large family of random, or a large family of code words corresponding to M, but again in a tree-like fashion, because of course, for any prefix, I'm going to have a large amount of suffixes. And it lends itself very naturally to this kind of causal setting, because if I know what's going on, let's say in this portion of the code, I still have no idea of what's going on later, because all these randomness, the randomness corresponding to each chunk is chosen sort of independently of the randomness of another chunk. So this method is, it's sort of useful for, in the sense that the future of the code word is independent of the past. So that's one type of encoding process in which we use randomness in the encoding. Another type of randomness that we use in encoding is just the addition of noise. So That also turns out to be pretty useful. We can take our message M and we can encode it to, let's say, a single code word. Let's call that C of M. But we can add to that code word some noise, and let's call that U of M. And the thing is that the noise that we add, again, this is only Alice is adding to the noise, and adding noise, of course, is gonna, it doesn't only confuse James, it also confuses the decoder. But this is gonna be, usually we add something which is very low rate noise, or sorry, low weight. The noise is gonna be low weight, but the more important thing is that the noise statistics will depend on the message M being transmitted. So I think I can draw this in an easier way than maybe explain it. So for every message M, let's say this is the code word corresponding to M, we're gonna add noise. Maybe this is the noise that we're adding. And if we look at another code word, we're designing this noise vector to depend on M. So the other code word is going to have a collection of noise which maybe has a different statistical pattern. So here the axis of the noise is like this. Here the axis of the noise is like that. And the idea in general is that in the decoding process, we can also try to use the noise statistics to identify which message was being transmitted. And we can show how to do, or we'll show where this comes in very useful. So James is very limited in his view. James is only imposing erasures, so it can't actually cancel out this noise. And so if James doesn't see well, or doesn't see where the noise occurs, then he becomes very limited, because now he can either erase locations and then we cannot use the noise statistics in those locations, or James can not erase those locations, but then if by chance there is a noise statistics there, it's going to be in our favor. So having this noise as the stochastic part of the code word, it also turns out to be very beneficial. Again, I know this is kind of vague, but this is sort of a common theme in many of the constructions that we have. Yeah, let me go on. And again, I know this is a little bit vague, and maybe I'm not getting many questions, so I'm a little bit concerned. But in general, I'm sorry, Prakash.
I'm sorry. I just wanted to say, don't be concerned. It's fine. This is for us a teaching seminar, so it's very good.
Okay, good. Because again, these are the high-level techniques that we're using, and I'll try to show. I know that I'm a lot over time than what I planned. I planned to be here in my notes to be like after 35 minutes, but I know that already an hour has passed. And so let me talk about a little bit about how we decode, and then a little bit about our converse proofs, and then I think I'll be able to at least put in one concrete result.
Good. Yeah.
So that I think will help. So again, the stochastic nature of the code words are these, essentially these two techniques, either that tree structure or the noise. Once we design our code for decoding, we use a scheme that we use that's conceptually we find it very useful. We find it very useful not only in this context, also in network communication or in the context of network coding. I've also found it very useful. You don't have to think of the decoding in this way, but again, we find it useful for the analysis, and also useful for the converse kind of matching converse proofs. So the decoding process usually goes as a two-step process. In the first step, the decoder uses some part of the code word, and if we think of the case in which we're causal, then we actually use some kind of prefix of the code word. So in the first step, we use a prefix, and I'll just stick with the causal intuition, although the same ideas work for the myopic. We choose a prefix and we list decode. So this decoding typically can be done very easily using typicality decoding. So even in these kind of semi-adversarial manners or channels that James has some kind of malicious flavor to it, you can still do typicality decoding and you can still list decode. But that, of course, doesn't allow you to communicate. You have to take the list and disambiguate it. So in the second step, we, let's say, use the suffix to turn list decoding into unique decoding. So we call this disambiguation. How do we do that? We have some kind of list. In that list, there are many messages. What we want to do is we want to have some kind of tournament between the different messages based on the suffix and decide, based on maybe the statistical properties of the messages and the suffix, some kind of a maximum likelihood or something of that nature. We're able to choose one of them and say that's the element that that was decoded or that was transmitted. So decoding is done in a two-step process. And again, this is very useful because also in general AVCs, you can look at list decoding bounds, or you can derive list decoding conditions, and which are relatively, again, just typicality decoding. And after you do that, you need to quantify this additional step of turning the list into a unique element. So not only is decoding done as a two-step process, but also the converse proofs or the jamming strategies that you want to show are also done in this kind of two-step manner. And let me do it the following way. Again, sticking to this kind of causal setting. If I'm a jammer and I want to confuse you with a different code word, or I want the Bob to have a decoding error, one way that we're able to do that is to, again, divide things into two cases or two steps. And again, this is kind of vague, but it's really the underlying idea of many of our techniques. In the beginning, the jammer, let's say, again, I'm using the causal setting. So this is the bits being transmitted one by one over time. And so what James does, what the jammer does is he's very conservative with respect to the number of erasures or the power that he's sort of wasting on this part. And he is maybe wasting a little bit of energy in erasing certain positions. But he does this up to a point in which, first of all, the block length, a large portion of the block length was actually used up. But secondly, he makes sure that up to this point, the only thing that Bob can do is list decode. So there's a point in time in which James says, okay, up to now, both me and Bob have a list. So the kind of first step is, we call this wait, or we don't do much until both James and Bob and the decoder have a list. If James waits too long, then of course, Bob is going to be able to decode maybe just from the prefix. But the thing is, we sort of carefully design a jamming process in which very little is done until both James and Bob can reduce their uncertainty to a list. Once we've reduced the uncertainty to a list, I'll draw that on the side. So maybe this is the, let's say, the correct code word that was transmitted. And maybe this is another one, and there are a bunch of others. Once there's a list that's shared between James and Bob, then James decides to symmetrize, meaning that James is going to choose a code word from this list and try to confuse Bob regarding these two code words. The advantage is now that we've made the remaining block length, right? So these two code words are consistent on the entire first part of the communication. But now the remaining block length is small. That's in James's favor. And confusing on a small block length, if you've preserved a lot of power, is an easier task. So in the second step, we want to symmetrize. So in the first step, we wait until we have a list and we choose the code word corresponding, a code word corresponding to M prime in the list. And in the second step, we want to symmetrize with respect to that code word. Let me just say what I mean by symmetrize. I think it's also beneficial to see that in general. And again, when we apply it in different places, the ideas or the underlying ideas are very, very similar. You wanted to ask, I think, Prakash, do you want to ask something? Or? I can't hear you.
No, I'm sorry. No, I did not have a question. No.
Oh, okay. I just didn't look up and then I saw. Okay.
Sorry, I didn't mean to scare you.
Yeah, I scare easily.
And yet you
Yeah, so
No, it's more my fault. Yeah.
So again, I want to give some kind of high-level understanding or high-level picture of what we mean by this second step of symmetrizing. The thing is that once we choose a code word, let's say that the code word corresponding to M is just X and the code word corresponding to M prime is X prime, then we claim that James can confuse Bob between X and X prime if the following procedure holds. And it's very similar to the standard AVC process of symmetrizability. Right, so James, or I'm sending, let's say, this is the original setting, I'm sending X. And James is choosing X prime from the list. Based on that, it's sending out some state. And again, if I do this in full generality, I get some outcome Y. We also have additional information going to James in the either causal information or noise information in the myopic case. So I want to say that James can confuse between X and X prime, and this is actually an n-letter process, but it can be turned into a single letter process. So James is confusing between X and X prime if the exact sort of mirror image happened when Alice sent X prime and James is picking X. So if Alice sent X and James is picking X prime and we get some distribution Y, if there could be another jamming procedure, which also James could do, that would have, in the case that Alice sent X prime and we picked X from the same list, would have given us also the same distribution on Y, that'll cause a decoding error. And so this process of waiting a little bit, designing a list, in the process of waiting, we've made symmetrizability easier because the remaining block length is now shorter. That allows us usually to design a jamming strategy for James. Yeah, I think it's a little bit vague, but I can now dive into concrete examples if
Sure.
if it works.
Yeah.
Okay. So let's show one of the. I won't have time for more than one, but I'm gonna just shift up a little bit. I'll look at the table, and I want to show one of these results because I won't be able, I think, to show more than one. But I think the one that I can show, maybe that'll give a lot of intuition, is the causal adversary giving 1 minus 2p capacity, both an achievability and the converse. And if I have time, I'll maybe show that why 1 bit of delay gives you a jump in capacity to 1 minus p. And I'll try to use the intuition that I hopefully built a little bit, both on the encoding techniques, the stochastic nature, and the list decoding, and disambiguation, or this two-step kind of converses or decoding process. So let me do that. Let me do the causal. So again, so James sees x1 up to xi when deciding no, I want to make a typo, when picking SI. And this is actually the part of this was joint work with Zitan, which is was done a number of years ago before he joined Maryland. So Zitan Chen, and also with Sid Jackie. So I want to show that the rate is 1 minus 2p, or the capacity is 1 minus 2p in this case. So we can show both we'll show both a converse and an achievability. And let's do the converse first. And the converse, so the method that this converse is going to be, again, a two-step method. It's the exact method that I presented previously, but it was actually applied for the erasure channel by Vasily and Smith a few years ago. So I want to show that I cannot communicate a capacity more than 1 minus 2p in this setting. And I want to do this again in this a kind of two-phase converse. So let's do the following. So let's assume that I have rate, which is a little bit larger. If I have rate, which is a little bit larger, in the first phase, again, I'm designing a jamming strategy. The jammer is just going to wait almost the full rate, maybe a little bit less. I have these epsilons flowing around, sorry, that are going to be a little bit confusing, but essentially the adversary is waiting. It's not doing anything in the first phase. Something like Rn locations. A little bit less. And so because I'm waiting a little bit less than the rate of the code, when I decode, or when I try to decode, I won't be able to, because I see less bits than what I need to actually decode. So both James and Bob up to this point are only able to list decode. So they can both construct a list which includes the correct code word. So let's call this X. And for the moment, I'm going to assume that our code is deterministic. It's just easier, but this can be extended to stochastic codes as well. And so there are many other code words here. But what James does is picks one of them at random. James has no idea what X is, but he picks just one at random. Let's call this X prime. So James constructs a list and just picks one element. Randomly in that list. Let's look now at what's going on here with respect to the numbers. So I've weighted something like 1 minus 2p plus epsilon over 2 times n. So what's left is almost 2p. That's the remaining part of the code word. And so this list here, you know, these code words are consistent on the first part. And so actually the only thing that matters is I can look at their suffix. So we can only look at the suffix, which is in this case of this length. And so I have, as an adversary, I have a power to erase a p times n entries. And all in all, there's something like 2p times n entries. And so I can erase half of the entries. So as an adversary, James can erase Pn on second half, on part 2. The thing is that Pn is even more than half of this because of this slight slackness that we put in here. So when can James actually confuse between x and x prime? So if the distance between x and x prime is less than or equal than Pn, then James can confuse, can cause a decoding error. So let's try to understand this Pn as a function of this block length. So the block length is suddenly shorter. It's almost half. It's not almost half. I'm sorry. It's a little bit more than half. So James can confuse or cause a decoding error if the distance between x and x prime is at most Pn, or in other words, if the relative distance, or if the normalized distance, let's write like this, of x is at most Pn divided by 2p minus epsilon over 2 times n. we'll get to the punchline in a second. This is something like 1/2 plus delta. So the bottom line is that if James chooses an x prime that is of distance, of relative distance, less than 1/2 plus delta from x, it can actually cause a decoding error. How can it do that? I can see, of course, it's seeing each and every bit of x being transmitted. If it differs from x prime, it's going to erase it. If it doesn't differ from x prime, it doesn't erase it, and it's able to cause a decoding error. But we know that there's no, this is a very large minimum distance. So to have a relative distance of 1/2 plus delta is enormous. And Plotkin tells us that any code of size or let's say the opposite, that the maximal code of minimum distance 1/2 plus delta is of size at most something like, I don't know, 1/delta. I'm cheating here with constants, but it's something like that. So what does this mean? So where are we? Yeah, time-wise, I know that I'm in trouble. So where are we? The adversary wants to is choosing x prime at random. It's going to be able to cause a decoding error if indeed the distance between these two is less than 1/2 plus delta. So we can view this as a graph, and I'll say this maybe a little bit faster in the sense that we can connect pairs of nodes by edges in the list if they're close together, again, closer than 1/2 plus delta. If we do that, we get a graph. That graph has a maximal independent set of size something like 1/delta. Because any subset that I take here, if it's of size 1/delta, or let's say larger, let's say 2/delta, if it's of size 2/delta, we know from Plotkin's bound that it cannot be of minimum distance 1/2 plus delta. It has to have some edge inside. So the maximal independent set of this graph is going to be small. And I know I'm saying this fast. If the maximal independent set of a graph is small, it's easy to show using Turin's theorem that the graph has many edges. If the graph has many edges, then with high probability, with high probability x, the red node here is chosen at random, x prime is chosen at random from this set. And there's going to be non-negligible, a constant probability that they're actually going to be connected by an edge. And if they're connected by an edge, then indeed I can corrupt as James. Yeah, I know that I'm kind of out of time, and I got a lot less than what I was planning to do. Yeah, but I still acknowledge the fact that I have to sum up. So I think that the sort of described in detail.
Thank you very much. Let me call for questions.
Yeah, I have a comment. May I?
Of course, of course.
So, Michael, this was a very nice talk, and I think you're being harsh on yourself by saying you didn't cover enough. This was very very clear and explanatory. they consider deterministic codes and the average probability of error, which means that James gets to see, knows the code book, but doesn't know the code word that's being actually transmitted, right?
Mhm.
So in effect, the can be investigated in these specific models. Sure.
And we do know usually that the amount of random bits that needs to be shared in these models in order to be able to achieve the oblivious capacity to go all the way to a very weak adversary, in many times it behaves like a logarithmic number. So it just means that only a very small portion of the block length needs to be wasted. And then you can establish common randomness, and then you can use the common randomness on the rest of the block length.
Right.
So I don't know if that's the system or the way that it was used in the work that you're describing, but if you can quantify the common randomness as being low, again, so it depends on what the capacity of the feedback is. If the capacity is 1 bit per.
Sure, I don't recall the proof that they had, but now I'll go back and look at the proof to see what's in the context of your talk. But that I think it was a nice result, which came after that body of the earlier body of work on AVCs, and the effects of feedback in many cases are not fully understood. So even if you look at it in the context of your model, where you in effect have the maximum probability of error because the jammer knows the code word, right? And then there are various constraints as on the jammer. So it's either jammer sees the code word causally or with a certain delay. And I don't know what implications feedback has in these cases, whether it can change the structure of the results in any significant way.
Definitely. So both in the case that the feedback is not perfect, and in the case that the jammer also can see the feedback, that's also something that could be
Uh-huh.
considered. So the feedback is hidden from the jammer.
Right.
If I understand correctly in the models you're
Yes.
thinking.
Yes, yes.
So I would like to ask something which may be completely silly. You have this jump with the capacity from 1 minus 2p to 1 minus p, depending on that unique bit. So my
Yes.
question is probably silly, but just it occurred to me. What happens if this James doesn't know the past at all, only that current bit? Can he use it perhaps better than the whole past, or it's completely crazy? I see that your converse proof here really uses that he knows the past. It's very important there. But I had the feeling that somehow the current bit is important, and I mean your result says that the current bit is important. The question is whether knowing only the current bit is something valuable for him or not.
So the way we designed the proof, indeed, in the list decoding phase, it's important to know the history in order to design this consistency set. In the second phase of trying to corrupt, then usually you're right. It's usually done in a single letter manner. So it really doesn't, once I have that list, now I don't need to remember anything about the past. I can just focus on the future.
Mhm.
But if for the entire process, you only see that bit, I haven't thought about that, but it seems extremely weak. I'm trying to sort of on the fly come up with a sort of encoding scheme that can get the oblivious capacity in that case. But I have to think about it. It seems extremely weak. Even you're saying just knowing the current bit.
Okay, thanks.
Yeah, you're a little bit stronger than oblivious, but still not very strong. Yeah, that's a nice question. Thanks.
Okay, thank you for the answer.
And my guess would be that it does not change it.
That it remains oblivious. I would also guess that, but I have to sort of work out the details.
Even though it's hard to say why.
Yeah.
Michael, thank you. This was a good overview and very helpful. Thanks.
Thank you. Thanks very much.
Okay, good. Thanks again.
Stop the recording.